So then we've got, I guess, like, what does it mean to have the first derivative? So, like we said, the first derivative is about the gradient of the tangent at a particular point. You will see the first derivative written as dy dx, f dash x, y dash. This can really be like any pronumerals technically, although most commonly it is y dash. But essentially, there's actually meaning behind your derivatives, and this is where applications of differentiation become super important, and it's super important that you understand these in order to do your applications of differentiation. So, we're going to say that we're notating our first derivative as f dash a, as sort of whatever we've put into, like the point is x equals a. So if our f dash a is greater than 0, what this means is that the gradient of the tangent is positive, and that means that the graph is increasing at the point x equals a. It's super, super, super important that you remember that when you're doing this stuff, this is looking at just a particular point. So we're just looking at x equals a as one particular point. We're not looking at the function as a whole. So yeah, if your gradient, your first derivative is positive, it means that your gradient is positive and therefore your graph is increasing. Then the converse to that, if your first derivative is negative, so it's less than 0, it means that the gradient of your tangent at the point that you've chosen, so say for this example at x equals a, is going to be negative, and that means that our graph is going to be decreasing at that point. And then the only other possibility is that if the first derivative of your point, so for us of f dash a is equal to 0, that means the gradient of our tangent is exactly equal to 0, and that there is going to be a stationary point at x equals a. So those are the three big things to remember about your first derivative. I think fairly self-explanatory with your first derivative, that if your first derivative is positive, then the tangent, the gradient of the tangent is positive and the graph is going to be increasing. If it's a negative, the gradient of the tangent is going to be negative and your graph will be decreasing. And then if you've got f dash a, or whatever your point is, equal to 0, your gradient of your tangent is equal to 0, and therefore you're going to have a stationary point because it's neither increasing nor decreasing. So yeah, fairly self-explanatory, that one, I think. And so then we've also got to think about the second derivative. So your second derivative is not going to be about the gradient, it's going to be about concavity. So for some of you, this may be the first time you're seeing second derivative. Essentially, you get the second derivative literally by differentiating twice. So, you differentiate whatever expression is first, and then, differentiate it, and then just do another differentiation again. Like there's no special rules to finding the second derivative. You literally just differentiate twice. And it gets notated as d squared y over dx squared, f double dash x, or y double dash. So yeah, whenever you see these two dashes, it usually means that you're looking at the second derivative of something. And so yeah, your second derivative is really important in telling you about concavity. So remembering that concavity is, concave up is our graph looking like this, concave down is our graph looking like that. So if f double dash a, so we're thinking about the point x equals a that we've substituted in, if the second derivative is greater than 0, your graph is going to be concave up at the point that you've substituted in. If your second derivative, so if f double dash a is less than 0, your graph is going to be concave down. And then if f double dash a is exactly equal to 0, there's a possible point of inflection. Now we will in a little bit talk about the use of the word possible. But if f double dash a is equal to 0, there's a possible point of inflection at that point. So we will touch on that possible soon. So don't worry about that just yet. So yeah, again, I would say fairly self-explanatory. If your second derivative is positive, your graph is concave up. In my head, positive and up sort of correlate with one another, which is why I say that's self-explanatory. Maybe you guys don't feel that in your head, but for me, positive and up go together and negative and down go together. So yeah. Now I'm going to show you guys a question, and we'll do a practice question about how you might see this sort of thing come up. This one's actually in a multiple choice question. So, at which point on this curve are the first and second derivatives both negative? So what I'm going to do is give you guys maybe like a minute to think about this question, and then we will go through it together. Okay, so hopefully you guys have had a go at this question. If you still need more time, you can pause this video and take as much time as you need. Also, if you guys are watching this and you've done the question and you don't want to sit around and wait, you can also skip the video ahead a little bit as well. So, at which point in the curve are the first and second derivatives both negative? So this is an example of a multiple choice question you might see. So we've got A, B, C, and D. So let's first think about the first derivative, and our first derivative is looking at gradients. So we know if we have a negative gradient, then we're going to have a negative derivative. So the first thing we want to see is which points have a negative gradient. So we know A is going to have a positive gradient, so we can cross that out. It's not going to be answer A. B will have a negative gradient, C will have a negative gradient, and D will have a positive gradient. So we can immediately rule out it's point A and point D. So then thinking about the second derivative. The second derivative is looking at concavity. So when our graph is going to be concave down, that's when we're going to have a negative second derivative. And so then from there, we can rule that point B is going to have both a negative first derivative because it's going, the gradient of the tangent at that point would be negative. And it is also concave down, as we can see in this point. Whereas point C has become concave up, which means that point C would actually have a positive second derivative. Therefore, B is going to be our answer option. Okay, and this question comes from a NASA sample paper as well. Okay, and so that's how you work out that question. And I guess it's just putting into practice the first and second derivatives and what they graphically represent. So then the other thing to think about with your applications of differentiation is stationary points, which hopefully you guys remember doing in year 11. So stationary points can either be maximums or minimums, or in rare cases neither, which is where like the possible point of inflection comes in. So there are two ways that you can determine the nature of a stationary point. So the first is the table of values. So essentially with your table of values, what you're doing is you're going to create a table. You're going to put your stationary point in the table and then do one number on either side of your stationary point also in your table. So let's say the stationary point occurs at x equals 3. you'd put 3 in the middle of your table, and then you do 2 and 4 on either side. Then essentially what you want to do from there is substitute each of those numbers into your derivative equation. So your f dash x, your y dash, your dy dx, whatever you call it. Once you substitute those into that table, you will then see, you'll get given each of the values for your derivative at each of those points. And then from there, you can tell whether something is going to be a maximum or a minimum. So the way that you can determine this is, so your stationary point, when you put that into your derivative, it'll give you 0. So essentially, you're going to have a maximum point if the lower point, so in our example, if we have 3 as our stationary point, your lower point of 2 will have a positive number be spat out, and then your higher number, so let's say 4, will have a negative number spit out, and that's how you can tell that you have a maximum. The reason for that being, at a maximum, your gradient goes positive, then flat, and then it'll go negative on the other side. And then the opposite is true for minimums. You'd have a negative, your 0, and then a positive when you're looking at those 3 numbers. And then you can also determine their nature using the second derivative as well. So in order to do that, you want to find the value of the second derivative at your stationary point. If your second derivative is positive, your stationary point is concave up, and therefore it's a minimum. If it's negative, your point is concave down, and hence it's a maximum. So when finding your stationary points and whether they're a maximum or a minimum, and thinking about which method do I want to choose to be able to, answer this question, I would usually pick the second derivative. I think it's quicker. Unless your second derivative is really hard to find, then I would do the table of values. I just find the second derivative is quicker. It is, I think, a little bit more foolproof, and that there's less room for human error, because you're putting less things in your calculator. You have to do less calculations, things like that. So unless your second derivative is really hard to find, which sometimes it is, it's got to be either really long to find, you don't know how to find it. If you're like me and you just don't want to find the differential of a log, then I would do the table of values. So yeah, table of values is just finding the value of the derivative near the stationary point, to the left and to the right. So what I want you guys to have a go at is this question. I always find it really weird doing questions from 2022, because this is the HSC paper that I actually sat. So it's weird to look back on it and be like, oh my gosh, I actually did this. But this is a question from the 2022 HSC. To find the global maximum and minimum values of y equals x cubed minus 6x squared plus 8, where x is between -1 and 7. So it was worth 4 marks. So these questions do have a fair few marks attached to them, and 4 may not seem like a lot of marks, but when you think about the fact that you only have 100 in total, it becomes a little bit I guess of a bigger deal, I guess. So it's 1/25 of your paper right there. So yeah, have a go at this question. Have a go doing it using the table of values if you can. And then I'll give you guys maybe 2 minutes or so. Feel free to skip ahead or pause the video if you need more or less time. But I'll give you about 2 minutes. Whoops, that's the answer. It'll probably take you longer than 2 minutes, but just for the sake of today's lecture, have a go for a few minutes. Okay, so let's have a look at this question. I'm going to give you a sneak peek to the answer accidentally. But the first step here is to find our first derivative. So if we've got the original equation, y equals x cubed minus 6x squared plus 8, what we want to do, bring that 3 down, x to the power of 3 minus 1 gives you 2, minus the 6 times 2 gives you 12x to the power of 2 minus 1, which is just 1. And then we know that that constant disappears. So we'll end up with y dash equals 3x squared minus 12x. Then, in order to find our stationary points, we're going to make this first derivative equal to 0, and we're going to solve. It's a fairly simple solve, so you get 3x by x minus 4 equals 0. And then your two solutions to that are going to be x equals 0 and 4. From here, we want to pop this into a table of values. So we've got 0 as our first stationary point and 4. And we've picked -1 as the lower limit, the lower number to 0, 1 as the higher number to 0 and the lower number to 4, and then 5 as the upper number to 4. Substituting each of those numbers back into our first derivative equation, we'll get 15, 0, -9, 0, 15. It's quite symmetrical, which is nice. That doesn't always happen, and it doesn't need to happen. Just like so happens to be that way because this is a parabola. So therefore we can say that x equals 0 is going to be a maximum because we've got a positive number, 0, negative number. X equals 4 is going to be a minimum because we've got negative number, 0, positive number. So then in order to find the actual points, we then find at x equals 0, substitute 0 back into your original equation in order to find the y coordinate that matches it. So you've got at x equals 0, y equals 8, at x equals 4, y equals -24. However, for 4 marks, you should recognize that that is not all you're going to need to do, okay? With HSC Maths, it's important that you sort of get familiar with how marks are allocated because it'll help you pick up that there is something else that you need to do in this question. First things first, this is question 22. Nothing is going to be that easy in question 22. Second of all, 4 marks is a lot for just finding maximums and minimums. At most, I would probably give that maybe 2 marks, 1 for finding the maximum, 1 for finding the minimum. So recognizing that 4 marks is a lot of marks will help you recognize that this question isn't finished. The other thing that'll help you determine that is that they've given you limits. So the next thing you actually have to do is check what's happening at your limits. So the endpoints, when we're checking them at x equals -1, y is equal to 1, and at x equals 7, y is equal to 57. So therefore, our minimum is -24, but our maximum is actually 57. Okay, so whilst the question told us that we had to find the global maximum and minimum values here, it wasn't actually through the differentiation that we found out that. It was by using the limits that they had given us to find that the maximum would be 57. The other thing that will help you pick up that your maximum is not going to be 8 is the fact that this is a cubic that's positive. So it's going to keep going up and up and up. So recognizing that if x equals 0, you still have to go up until 7. Okay, so we're not at the highest point just yet. Okay, also recognizing that your minimum and your maximum values are actually y coordinates. Your maximum is not at 0. While x equals 0 is a maximum, the global maximum point is not 0. The global maximum point is, well, in this case, it's actually 57. It's the y coordinate that is associated with the x, okay? Always remember that your global maximum, your global minimum are going to be the y coordinates, not your x coordinates, okay? Also, just remember, in order to find the y coordinates, you do need to sub them into the original equation. It's another mistake a lot of people make, is that they try and find their y coordinates in the first derivative, and your first derivative is spitting out gradients, not y points. Whereas in this, you're finding y equals, okay? Like you're literally finding y. So always remember to do it in your original equation if you're trying to find a value for y. And so yeah, this is just another like explanation of using the second derivative to find stationary points. Fairly simple. Find the value of your second derivative at the stationary point. If it's positive, you're going to have a concave up, which means it's a minimum. If it's negative, you're going to be concave down, which is going to be a maximum. So yeah, I think using the second derivative is much easier and much quicker if your second derivative is easy to find, of course. And so the other thing we want to think about is that points of inflection are going to be the points where the concavity of your graph changes. So your points of inflection possibly occur where the second derivative is equal to 0, but this is where the possible comes back. But you also have to check that the concavity changes using a table of values. Okay, because your point of inflection is the point where the concavity of the graph changes. So this might happen when there's a second derivative that's equal to 0, but it also might not. So always important to check that your concavity has changed on either side using the similar method to like a table of values. So, you know, put your second derivative, whatever's equal to 0, in the middle of your little table, and then, you know, do a number higher, a number lower, and then check your second derivative instead of your first derivative in the table as well to check that your concavity has changed. So then we've got horizontal points of inflection, which is just like another application of points of inflection. So if a stationary point also happens to be a point of inflection as well, then this is what you call a horizontal point of inflection. So this is when we have a stationary point. This stationary point is also a point of inflection, and therefore you call it a horizontal point of inflection. Same thing, there'll be a point about here as well, where you've got a point of inflection, but at this point it's not stationary, which means it's not going to be horizontal. Okay, that's really all there is to that. And so all of this stuff that we've done so far is all useful for curve sketching with differential calculus. So I guess this is where you the culmination of your differentiation stuff is being able to sketch using differentiation. Now, if any of you guys are like me and you hate sketching, trust me, doing curve sketching with your differentiation is so much easier than just like your regular, like, let's draw a circle. So yeah, all of this is with the aim of helping you to sketch. So that's not the only application of differentiation, but the big application that you're sort of working towards in Year 12 is sketching. So we're going to look at a question. I'll give you guys a few minutes to have a go at this. If you were doing this question properly, it would take you more than a few minutes. So if you do want to have a proper go at answering this question, pause the video. Otherwise, see what you can do in the next 2 or 3 minutes, and then we'll go through it together. Okay, we might go through this question now. If you do need more time, feel free to pause the video. Otherwise, let's get on with it. So looking at part A, so consider fx equals x cubed minus 3x squared plus 3 within the domain of x is between 3 and -1. So for 3 marks, we want to find the stationary points and determine their nature. Fairly straightforward question. So first thing we've got is fx equals x cubed minus 3x squared plus 3. Find your first derivative, so bring that 3 down, do 3x to the 3 minus 1. Then we do 3 times 2 and we bring that 2 down, x to the 2 minus 1, and that constant disappears. So our first derivative is going to be 3x squared minus 6x. Then let's do the same thing for our second derivative. Again, it's literally just doing differentiation on the first derivative. So we bring that 2 down, 3 times 2 is 6x to the 2 minus 1, which just gives us 1, minus 6 as well for the second derivative. So to find our stationary points, we make our first derivative equal 0. So we get 0 equals 3x squared minus 6x. Then we solve that, we'll get your stationary points are x equals 0 and x equals 2. First, when x equals 0, our y point, which we found by putting back into the original, is going to be equal to 3. And at that point, f double dash of 0 is equal to -6. Because it's less than 0, this is therefore going to be a maximum stationary point or maximum turning point. Doing the same thing with x equals 2, we pop x equals 2 back into our original equation, you'll get y is equal to -1. Substituting 2 into our second derivative here, we're going to get f double dash of 2 is equal to 6. And because that is greater than 0, this is going to be a minimum turning point. Okay, that's all you really need to do there. So for part B, finding the points of inflection, we're looking at our second derivative, which luckily we've already found. So we're going to find our point or points of inflection when second derivative is equal to 0. So therefore, when 6x minus 6 equals 0, and then fairly easy to solve that, x is equal to 1. Then, of course, we're going to check what y coordinate is associated, and we're going to get 1. Then we need to check that our concavity actually changes, because this is not enough to prove that we have a point of inflection. So what we do is, in our table, we have our x values on the top, we have 1, and we've decided to use 0.5 and 1.5 on either side of 1 to check concavity. Then we substitute each of these x points back into the second derivative, because we're looking at concavity. We get -3, 0, 3. And because the concavity changes on either side of this point, we can therefore say we're going to have a point of inflection. Now for part C, sketch the graph of y equals fx showing all features, don't find the x-intercepts. This is when you can start to plot all your different points that you've learnt about onto your graph. So we found where is our point of inflection, we found our maximums and our minimums. The other thing you want to think about is your y-intercept. Don't have to worry about the x-intercepts, but do worry about your y-intercept, and you should end up with a graph that looks like this. Okay, so the only thing that's not been plotted properly on here is 1, 1 being our point of inflection. I should have plotted that. Whoops, so that's a mark gone. Like if you don't plot like all your features, usually it is a mark gone for each of the features you don't plot. So that'd be 1 gone there. You'd also want to keep that 1, 1 there, but you've learnt about where your maximums and your minimums are. So we've plot each of those in, and then always want to find like where you start, where you end as well. So yeah, then you can